Welcome to the last video of this course, which is on a topic which is more of a side topic and which is called the regular version of the conditional distribution. I will tell you in a second what that's about. This will probably not be part of any exercise because it's a bit special, but still I want to do this here because it's at some places important that you know about something which exists. Okay, let's see what it is. So, the regular version of the conditional distribution. The most important thing is that you understand that there is a problem. And that's the following. We introduced the conditional probability like this here. We would now like to have that, okay, I can plug in sets in at the first place here, which are then conditioned on G, and that's a random which depends on omega. And I would like to have that for at least almost all of these omegas here, that's a proper probability distribution in the first variable here. And you might think that that's already okay, but the problem are these null sets which I have here because, well, I have defined this also only apart from some null set. So here's another version of this problem. So, well, take a countable set of sets, AI, AJ, all disjoint, and I would like to have that the probability of the union equals the sum of the probabilities. So like this here. And you have this because, well, the conditional probability of the union given G, okay, you can write the probability as the expectation of the indicator. You can write because of the defining equation for the conditional expectation, this as this here. Because they're disjoint, the indicator of a union is the sum of the indicators. The indicator I can pull out of the expectation. And then I can argue back and say that's the sum of the expectations of the conditional expectations, and then I can plug in the sum again, like so. Then I have shown that these two things here are the same. At least they are the same, almost surely. So for P almost all omega. However, the exception null set might depend on the sequence of the AJs. And that's not nice because there are uncountably many choices of such infinite sequences of AJs usually. And that means you do not have this here where the first variable is a free variable because there are too many of these null sets. Only a countable union of null sets is a null set, we know this. But here I would have an uncountable set of null sets and their union doesn't have to be a null set anymore. So that's the problem we would like to solve with this regular version of the conditional probability. So we'd still like to have that we can make sense of this, that for P almost all omega, this here is a proper probability distribution. And yeah, it works on nice basis. That's the next slide. But here I'm going to explain to you what we want to have, which is a so-called stochastic kernel from F, which is my ground space, to some other measurable space. That's the following. That's called kappa. The first variable is an omega, and the second variable there is a set. So it's from omega times F prime to something, which is a probability. For all omega, it's a probability measure in the second variable. So that's exactly what we want. At least we want this for at least almost all omega. And the other thing that we need is that for a fixed set here in the second coordinate, it's measurable with respect to the first coordinate. And then we can say what a regular version of the conditional distribution is. Let's say we want to have it for a random variable y given j that is some stochastic kernel like this here, such that this here holds. At least it holds for p almost all omega and every b in f prime. So every here and almost every in the first component. So yeah, given j, that's a probability distribution on what the y does. Okay, so we want to have exactly some kernel like this here. And the answer is as follows for the question that we asked in the beginning. If, again, we had this, ER is a complete and separable metric space, and Y is E-valued, and G is a subsigma algebra of F, then there exists a regular version of the conditional distribution of Y given G, which means, stated differently, that I can take this null set here in a way such that that's one null set for every choice of A's I had here. That was not clear here, but on nice spaces, which are again complete separate matrix spaces, I can do this and I can have the regular version of the conditional distribution of Y given G. Okay, that's it for today. It was a nice course. Hope you had fun, and maybe see you in the next course.